Hello, good morning everyone. Glad to see a lot of people came after partying hard last night. So it's my pleasure to introduce Ian Foster, who is the Director of the Data Science and Learning Division at Argonne National Laboratory and Professor of Computer Science at the University of Chicago. I think everyone knows him for his work in distributed, parallel and data-intensive computing. So thank you very much for joining us.
Thank you. I think this works. We'll see. So thanks a lot. I'm here to talk about, so I'm not a synchrotron scientist, although I have some friends who are. So this is a picture you've probably seen before of, you recognize the advanced photon source. Not quite as nice a setting as here, but still okay. But I'm from the other side of the campus, the computing part of Argonne. Not actually in the leadership computing facility, but that's where we are. And we're about 1 kilometer away, or as we like to say, being computing people, 5 microseconds. So why do I mention that? Well, we're at a time where computers are connected to each other and to facilities at increasingly fast speeds, and so it starts to become feasible to build various forms of instruments that link a computer in one place to an instrument in one place to a facility, computing facility somewhere else, and perhaps to a decision logic in a third place to enable smart instruments that process data as it is being generated rather than after it's being collected and taken home on a floppy drive or USB stick or whatever it is that you like to use. And why is that important? Well, because of course, as we all know, we live in interesting times. This is a somewhat old slide, but points out that we're in this fascinating period where data rates are increasing exponentially with a high coefficient. Computers are getting faster also. Sadly, the number of researchers is staying flat. And computational methods are, of course, improving in ways that allow us to do more interesting things, but they also are increasing in complexity as well. In some ways, that's also calling for more computing requirements. So, and here's a slide that Hannah Paraga put together, and she has a talk later today that will say more about this. But just as an example, we're well aware at Argonne that we're going to have orders of magnitude more data in the very near future. So we're there, right? Just with the upgraded facility coming online, and while it may perhaps previously used to be perhaps suboptimal, but still feasible to store your data, take it home, and process it there, it's increasingly no longer a reasonable or feasible thing to do. Okay, so just a few words about exponentials. So we have more and more data, as you know. As a friend of mine, Alex Saleh, says, well, if you have exponentially more data, then you have to process exponentially more data to produce a good paper, unless you're going to throw your paper away. If we don't do that, then we're going to be innovating exponentially less, at least relative to our colleagues who perhaps are managing to make sense of that data. If we keep using exponentially more computing and exponentially fast or better methods, we can hope to keep up. If we want to do better, we've got to do something even better than that. And that might remind you of the Red Queen in Alice in Wonderland, who said, it's if you want to keep still in Wonderland, you have to be running very fast. If you want to get anywhere, you've got to run even faster than that. But anyway, let's move on. So the topics I want to talk about today really are three. First of all, I propose that in order to make effective use of these vast data volumes from synchrotrons and other scientific facilities, we need to be able to connect in real time to computing, storage, etc. And we can't reasonably do that only within the scope of a single machine room. We have to be able to reach out across the world of science. Secondly, in order to make effective use of those once we're able to connect things together, then we need to find ways of building what you might call workflows, systems that will link instruments with computing and so forth. And I know there was a workshop earlier this week on that. I'm going to talk about some techniques we've been using. And then finally, at the end, I'll just say a few words about how new AI methods may change some of the things that we're doing here. But first of all, let's talk about this notion of a universal data and computing substrate. So that's something I've been working on with my colleagues at Argonne and the University of Chicago and elsewhere for a long time. The notion is if we are going to effectively compute using local and remote computers, if we're going to link researchers with data, we need to be able to act on resources regardless of where they are located, regardless of what interface they have. So we've developed things I'll say a bit about called the Globus Connect and Globus Compute agents that we deploy in actually tens of thousands of locations around the world now. Then we need to be able to execute remote actions on those entities reliably, and we've shown that you can do that by using a combination of central cloud management services for highly reliable, persistent management, and then the management being devoted to operating on the local agents. And then so finally, something I won't say much about but is very important, you need to be able to manage who is authorized to act on these resources. And increasingly, if you're running complex workflows, you need to be able to have programs that will act on your behalf on remote locations. And so you need capabilities that people in the biz often refer to as delegation, the ability to delegate in a controlled manner authority to programs that you're going to be running. So we've developed out the Globus system over the last 14 years or so. I won't say too much more about it, but point out that now at this point controls some 60,000 endpoints around the world in more than 80 countries, more than 500,000 registered users, and is used to move a lot of science data around. But rather than talk about the details, I thought I'd show you a little video, if you don't mind, that I made about a year ago. So I think it's fun. We'll see if you do as well. So this is an odd sort of picture. It shows the size of a transfer here, the great circle distance from source to destination here, and you'll see a growing number of these little dots, each of which represents one transfer. This is about a 10 gigabyte transfer over about 2,600 kilometers, and the color shows the speed. So this is about 50 megabytes per second, perhaps, not a very impressive performance, but we'll see it get better over time. And then the video, if I can make this work here, I think I can. Right, so now we're going to see the transfers performed by this Globus server since 2010 or so. Each of those dots represents a transfer. You can, over time, you can see some interesting things. Obviously, most are still, oops, I think I hit the wrong button. There we go. Keep going. I want you to see it, so we're going to do it again. Okay. I think I can do it. Let's see. There we go. Okay, good. So you can see most transfers, of course, are close to home. Some are far apart. Interestingly, there are very few transfers between sites about 5,000 kilometers apart because of the oceans that get in the way. A few out over here, which are mostly tend to be from Australia or New Zealand to Europe, but perhaps some other pairs of sites as well. And if you look carefully, you'll see that as over time, we're getting up towards the end of the 2020s now, things get increasingly purple as people manage to deploy faster networks and work out how to use them better. So by the end of this period, which finishes in about 2023, I've highlighted a few things here. I think I saw one Lyon here. Or maybe I can't see it.
You see Grenoble there. Yeah.
Grenoble, you see Grenoble?
Yeah,
Oh, there it is, yes. Grenoble, No, that's Greenbelt, US to Urbana. Yeah, anyway, not quite the same thing, not as pleasant at all. Anyway, so that's, this gives you some sense of how global science is. I think this is exciting. And then I did look for a similar one just for French hosts, just for fun. And there I think you see, oops, I keep pushing the wrong buttons. This is embarrassing. Here you can see, there's Fontaine to Lyon and maybe some more further away. I can't read what that says there, but somewhere in New Zealand is communicating with France as it should. Okay, let's move on. So that's what Globus looks like in terms of the traffic and communication that occurs. Now let's look at what it looks like at a particular facility, the Advanced Photon Source and the Leadership Computing Facility. So I'm sure you're quite familiar with the Advanced Photon Source. These are all Globus transfer endpoints. These are agents that are set up to allow movement of data to and from beamlines and to remote locations. And these are our various computers similarly configured. Increasingly now we're deploying also Globus Compute endpoints, so you can do remote computing. And something that you may hear more about this afternoon, also so-called service accounts that let people act on computers in a controlled manner without having to have a local account, which is really important for, of course, the sort of remote computing we want to do. And then this is what allows us to do the interesting things, which is deploy workflows, which I'll say more about in a minute. Okay, so that's a few words about this notion of a global compute and storage fabric. So the key point here is we've enabled, by deploying this combination of central cloud-hosted services and with a quite sophisticated security and authentication system, and then these many local agents, tens of thousands of them, we make it possible to be able to compute anywhere that has one of these agents deployed and move data between any pair of sites that have these agents deployed. So now let's look at what we want to do with this global fabric. And this is when we come to building pipelines that link such devices. So we've heard earlier this week, some of you, and we've heard in other cases about various workflow tools, and there's, by some counts, several hundred workflow systems that have been developed over the years. I once heard it said that every PhD student in computer science produces a workflow system. I certainly produce more than one, so I'm above this. But the interesting thing in many of what's nice about sort of light source data analysis is often the actual logic that you want to implement in terms of actual flows are not that complicated, but the hard part is being able to authenticate to, connect to the different resources that need to be linked together. And I'll show you an example of that in a minute. Anyway, so let's give you an example, though, of what sort of flow we might want to discuss. This is one we've been developing with people we developed some years ago with people at SLAC, at LCLS. It's X-ray photon correlation spectroscopy, I think it is, data analysis. So of course, they have a high data rate facility there. They've worked out how to use deep learning methods to do accelerated analysis and detection of peaks in the data. The problem they face is that retraining this model takes 20 minutes or so on their local GPU. So of course they could buy their own computer, but maybe they don't have resources. But so we on the other hand at Argonne have a very fast system, a Cerebras CS2. This is a wafer scale deep learning accelerator. And so simple math, if we transfer the data from SLAC to Argonne, we can do that in 7 seconds. We can retrain the model in 19 seconds, transfer the trained model back in 5 seconds, and end up retraining in 35 times faster simply by moving the data back and forth. So, and I think we're going to see increasingly often these sorts of interesting trade-offs between time and location, where computing remotely is beneficial from various aspects of performance. So if the flow here obviously is then to simply collect the data, move it to a remote location, retrain the model, then deploy the model. We'd like to be able to implement and run that flow repeatedly. So how do we go about implementing these flows? Well, that's a question we've been looking at for over the last few years, and the hypothesis is that we can capture these sorts of patterns in common and reusable fashion. So, for example, here, some patterns. We've got data collection and transfer, AI model training, AI model deployment, and then later on inference on the model. So we could implement each of those in a little piece of logic, parameterized with the location where it's going to occur, for example, and then map each of these to a computing resource and a data and a storage resource. Any resource basically that has got one of these Globus endpoints on it, and then go ahead and run the flow and observe what happens. And that's a pattern that we hypothesize we should be able to repeat in many different settings, and indeed we've been repeating it quite a lot, as I'll show you. And I would like you to take a minute to admire this lovely cartoon I found, which maybe captures our goal. This is Sisyphus, of course, who's tasked with rolling a rock up the hill forever, but he has a robot doing it, so he can sit there and read a book. So maybe that's symbolic of what we're trying to do here. But this, by the way, is a little series of. We'll look at this in more detail later, but this is from the bottom up a series of steps in one of these flows. So what are we doing here? It's publishing data and then completing. So this is the end of a multi-step flow that involves data publication. So let me go on and look at what some of these flows might look like in other settings. So these are some of the things that we might want to be able to capture in these series of steps that we want to be able to implement, archive, and reuse. So we want to be able to capture data, process it in various ways, store it, extract metadata. We probably want to involve humans in some steps, in some cases. We need to be able to assign persistent identifiers to data, control who's able to access it, publish it in ways that others can perform operations on it. So the flows involve a quite wide variety of actions of different sorts. Some involving lots of computing, some involving lots of storage, some involving more interaction with humans. So here's a detailed example: our XPCS, another XPCS flow, which in this case involves, as you can see, there's data transfers, some various analyses, some data publication, and access control setting, and with ultimately the data being available in this interactive portal. What have we got next? Here's another one. This is a cryo-EM flow, which in this case involves, oops, I pushed the wrong button again, a human interaction step, which seems to be quite common. People want a human to verify quality of data before publishing it. But each of these steps, as we'll see, can be translated into an operation on one of these remote agents that I've talked about, either a compute or a storage agent or some other agent that we are able to populate in this framework, and then the overall logic can be managed by this cloud-hosted, performant, reliable coordination framework. Okay, so I'll give you another couple of examples. See what I got here. So one thing you can do with these things, of course, as I've shown already here, is run across. We can run these things on at a single site between APS and the Argonne Leadership Computing Facility. We can run across multiple sites, between SLAC and Argonne in this case. What else can we do? We can as we've been working with Steve Hinke and others on his, I don't know how to pronounce that word, but someone here probably can, Tychogus. we've been we're demonstrating, along with people at APS and LCLS and ALS, that we can easily retarget flows to collect data from different places and to perform computing in different places. If you looked very carefully at this here, you'd see this is the last steps of a flow. Well, here's the flow down here. Oh yeah, so we're looking to see where data is available and selecting where to compute based on that information and on the availability of computers, transferring input to the remote location, performing the analysis using the Tycogos package, and then transferring results back. And in this case, we're able to show we're taking data from 3 different beamline data formats and running it at 3 different locations. And if you could read the fine print here, you'd see this would be the results of large numbers of such analyses. Okay, so we've been running this flow management logic at Argonne and at a number of other sites now for some time. This is a part of the Globus flow management interface, where I think we can see down here, that's right, we can search for flows labeled that are accessible to this particular group of people, that are labeled APS, XPCS, SSX for serial synchrotron crystallography. So you can see there are tens of thousands of flows have been run over the last several years. Not in the last year for obvious reasons, because of course APS has been down for its upgrade. So if we look at some of our, so here are some of the flows that, oh, I pushed the wrong button, no, there we go. Here are some of the flows we've implemented: XPCS, serial synchrotron crystallography, tychography, high energy diffraction microscopy, and then here are some of the usage results through roughly the end of 2022. Then we stopped because of the upgrade, and we're just getting started again. So we don't have more recent usage results, but of course the underlying flows software has been running at many other sites during that time. And you can start to get a feeling for how these different applications make use of computing. So this shows data transfer times in blue, compute times in orange, cataloging, so-called search, in green. That's not really visible. So these are all on-demand computing requests being made while the flow is running to, typically in this case, computers at the Argonne Leadership Computing Facility or our lab computing research center. So an important capability that we require in order for these things to be able to achieve this on-demand rapid computing is the ability to access computing resources in an on-demand manner, rather than waiting for hours or days for computing to become available. So the Argonne Leadership Computing Facility and a few other facilities we work with have set up to allow such sorts of interactive access, on-demand access, by manipulating the queues on their systems. How that will work out on the long term, I think, still remains to be seen. Oh yes, and so I'll just mention we've also got various tools for, I did it again, for, sorry about that. The mouse has got a short cord. Various tools for creating and manipulating flows, which I won't spend any time on, but point out, if I'd given this talk a year ago, we would have shown the lovely Python programs you would write to do these things. Now we can point to the graphical user interfaces for browsing flows that you've created or run, looking at the actions involved in that particular flow here, and also configuring and setting up the compute endpoints where you want to perform the actual computation for the computational steps involved in your activities. And one more thing I'll mention on the sort of infrastructure side is a vital, in all of these activities, in order to be able to manage these sequences of steps, you have to be able to, of course, invoke via some API the operation that you want to perform. So the Argonne Leadership Computing Facility has set up a large storage system that supports Globus APIs, so you can automatically upload data, query catalogs, download data, set permissions, and so forth in a programmatic manner. And that then makes it trivial to integrate these operations into the flows that we've talked about. So when someone, for example, processes some serial synchrotron crystallography data, the flow will not only perform the analysis, extract metadata, and then upload the data to the location where we want to store it, looking something like this perhaps. This is serial synchrotron crystallography, but also be able to set the permissions and index the data so other people can find it. Okay. One thing we're starting to do that I'd love to talk to people about is incorporating into these flows not just manipulation of bits, but also manipulation of physical hardware by incorporating instrument control. I won't say more about that, but it's, I think, an exciting direction for the future. So this is a beamline at the APS that has some remote control capabilities. Okay, so that's those are the first 2 points I wanted to make. So universal substrate allows us to then implement these flows that link experimental facilities with computing, storage, etc., using these sequences of steps that are encoded in ways that are reusable for different purposes, as shown, for example, by the PyTCoGAS set that can target different beamlines, different facilities, and different computers. But now I want to say just a few words about how things may evolve as we go forward with the development of AI methods. So probably everyone knows that AI is the future, or maybe something. Maybe we will see. But there's certainly, I think, my view is that it's quite likely that as we learn to leverage these so-called foundation model technologies that have proven so effective in other fields, and apply them to materials design and biological data analysis and other applications, and perhaps also apply them to problems relating to design of experiments and analysis of results, that we're quite likely to see significant improvements in our overall productivity and perhaps more rapid pace of discovery, which would be good given that we're, as we noted earlier, dealing with these exponential increases in problem complexity and amount of data that we're dealing with. So we ourselves are using these methods to design experimental protocols, and I'll just play this fun thing here. I think if I can get it to work. Let's see. This is a young student at Chicago, Rory Butler, who's not using it. This has got nothing to do with synchrotrons, but and you probably can't see the fine print, but basically it's in a simulated world. First of all, created using a technology called Omniverse. He's designing, is trying to come up with protocols that will allow for the control of this experimental apparatus. There it goes. And if you will look very carefully, it tries things, and then sometimes it finds mistakes. Let's see if I can stop it there. No, I can't do that. So it finds mistakes, and then it might, for example, find that it's trying to stick something into this piece of apparatus, but doing so when the lid is not open. So it can detect that using a camera and then wind back, change the protocol, and try again. And over time it evolves a successful protocol to perform this particular experiment. So obviously we don't want people experimenting with synchrotron light source beamlines, but if you have the appropriate simulation, you can learn a lot, evolve protocols simply by using a digital twin, as here. And then, well, at least for the simple lab protocols we're working with, we're able to then deploy them in the lab and test that they work in practice. So we think we're able to reduce greatly the cost of and the time required to develop a new protocol. So one thing I think we should all be thinking about is, and we are working with some collaborators at Lawrence Berkeley and Diamond and elsewhere, is how we can combine data from various experimental modalities from many sources and then use those to train foundation models for various types of systems. So that's lots of interesting opportunities in terms of applications, but these new methods also create substantial new demands for computational workloads. So training of foundation models can consume thousands of GPUs, tens of thousands of GPUs. Our Aurora system at Argonne, which has 60,000 GPUs, is, well, at the moment we see this big competition going on between the traditional simulation scientists and the AI scientists they both want to use all of the machine all the time for different things, and luckily we have a peer review process for deciding those allocations, but it's a challenge. And then once you get these models trained, then inventive scientists find ways of using them in their research. So they'll say, I want to be able to ask this model a question about this particular material. And often you get back interesting results. But of course you think, well, then I want to ask it about 10,000, 100,000 materials. And there you've got a whole new, very substantial computational workload that needs to be supported. So that's a challenge for those building computing facilities, and I think perhaps also for those operating facilities such as ESRF and similar systems. If people need to be able to use these AI methods to make really good use of your facility, then where are they going to find the computing resources to train the models in the first place and then to perform the inference tasks required during runtime? Okay, so to summarize, these are sort of the points I wanted to make. The changing nature of experiment and computation means we need increasingly to compute on data during, not after acquisition. I think probably everyone is familiar with that challenge. And I've suggested three things. They're sort of infrastructure things, but important things. On-demand computing, so you can perform analysis when you need it, or perform AI model training or inference. A universal data compute and authorization fabric, so that you can link resources rather than being forced to either run your own resources or locally or negotiate special treatment every time you want to do something remotely. And then cloud managed reusable flows for reliable execution. If every flow is the passion project of an individual scientist that only works on their data and their facility, we're not going to be able to make progress. So, we are enthusiasts. I'm enthusiastic, of course, of the Globus platform for doing these things. There are other ways of doing things, I'm sure, but I'd love to talk to you if you'd like to learn more about how we could extend and apply our technologies. But some of the things that need doing, I'd say, in order to make progress here, I mentioned 4. So we need some sort of universal data compute authorization platform. I think that isn't hard. It just needs will to force policies to be defined and software to be deployed. We need to build a community of people that are going to code, deploy, and evaluate these patterns, the patterns that perform model training, data analysis, etc. We've got a wonderful technology out there for data analysis, in the form of GitHub and so forth, and Python. But now we need to do the same thing for these reusable flow patterns, and that needs, of course, effort, but also needs effort plus commitment. And we surely need more computing, which is luckily not something I spend my days worrying about, but someone needs to, so we need budget for that. And then I think in order to advance AI as a technology for light source science, we need to overcome current barriers to sharing data. So I was told last night that ESRF has a wonderful data solution. Data becomes available to people for analysis after a certain period has passed. That's not true at many US sites, and I'm sure there's still more to be done everywhere to make data available in a form that we can actually train useful AI models on it. Okay, so those are all my remarks. I've worked with a lot of wonderful people. Raf may be here somewhere. Hannah is here. Nicholas is there somewhere, I think. Yeah, there he is. Good. Okay. And a few others are not here, but we have a great team working on these technologies, both developing them and deploying them. So thank you.
Thank you very much, Ian. Does anyone have any questions?
Thank you. Thank you for this very inspiring and future-oriented talk. And my question, I was, so to say, alerted by your comment that authentication is difficult when accessing to remote data. And my comment would be, what if we make all scientific data, especially the one that is produced for public funds, open access and open, and then authentication problems should, well, not go away completely, but become much easier.
Yeah, so certainly, well, if your data is not open, there's a whole set of other concerns, that you may have in controlling access. But most of what I'm concerned about, or we're concerned about, most of the data we work with is open, although perhaps not immediately upon the time of generation, which is a concern. But you still need authentication and authorization for controlling access to computers for deciding who's allowed to write the data, even if you're not concerned about who's allowed to read it, etc. So the problems don't go away, but they perhaps become a bit simpler. Yeah.
Thanks for the presentation. I'm wondering if, you demonstrated that you can acquire data on some places in the world, transfer them, via Globus, to another place, your supercomputer facility, for example, process them, and then send the result back, which is, the figures you showed are really impressive. But I wonder if your graphics for the time used for sending the data, processing them, so the processing is apparently still much longer than the transfer, and then sending the result back. Did you do the same, not in time, but in energy?
Okay.
Because we live in a finite world, finite planet, and the amount of energy for transferring those huge amounts of data from one place of the world to another looks to me, well, and it's exactly the opposite of what edge computing is supposed to be.
Yeah.
So well, if you have some figures.
Interesting. I mean, there's many things I could say about that. But we use the Slack example, and actually, I mean, the purpose of transferring the data in this case was to train a machine learning model that could be deployed at the edge for detection of interesting events. And that model is far more efficient than the previously used computational techniques. So in that sense, edge computing is being used to reduce time and energy demands. In terms of so I emphasized in that example certainly the optimization for time. We can also optimize for energy, and then the trade-offs may be different. So, but often, a large central facility can be more energy efficient than many edge facilities. It can use more cleaner energy sources, or not. So that's, I think, a good thing to be considering. I'm always proud of the fact that Illinois is, perhaps like France, a large amount of nuclear energy, which is unusual in the world. Maybe Illinois and France are like that. But yeah, anyway, we have time for, you're the boss, so yeah.
Thank you very much for the presentation. If I understood correctly, for ongoing experiments at the beamlines, you have kind of priority queues to reduce compute latency. At European Expo, we started off with that, but quite quickly got requests from users to actually have also static node reservations at their disposal at will. Do you have similar requests or similar concepts?
Yeah, I think I'm not sure how we're going to work that out. So far, you know, the on-demand queues, so-called, are working well. But I think when we've got all 60 or so beamlines running, that may no longer be the case, and then we'll have to see how that works out. I mean, it's largely a policy. It's a policy question. So you're suggesting a different policy solution. It's also, in some sense, partly a budget question. Who's going to pay for? Who's paying for the computing? Which is above my pay grade, fortunately, but is important. That's Nicholas's concern. Not really, but yeah.
Hi, thanks for the talk. I have a question connected to Globus. I mean, as I understand it, you can use Globus for workflows involving things like instrument control, raw data transfer, data refinement, and then data analysis. Now, normally at the end of this process, users normally have to do a sort of finer analysis of the data, and there are workflows associated to that finer analysis.
Yeah.
Can you do that with Globus?
It's not something we've tried. I think, you know, there's people have built very sophisticated applications, you know, using a wide variety of workflow systems, and for us, I think we would think of that. That's something. That's a node in our little graph of applications of data curation steps. You know, collecting your data, extracting metadata, performing analysis, publishing it. So I think different workflow systems are good for different purposes.
Okay. Thank you very much, and thank you very much for the conversation last night. You mentioned budget. I think you mentioned as well that there is kind of like a reservation for the instrument. So what's killing me in Switzerland is now the costs and also the service level agreements. So budgets aside, as you say, it's above our pay grade. But what kind of a service, you know, sync facilities, they feel that they are 24/7. Do you have to offer that service as well to actually make sure everything is available all the time for them?
Yeah, so those are fascinating questions. So you've got your precious few hours of experiment time, and so what are your options? So you can. One thing we're working on is the ability to dynamically route computing tasks to different locations, so that when one is not available, another one is available. It may be that one will need to, given finite resources, dynamically choose to use different methods depending on what resources are available at a particular time. You know, so I guess the worst comes to worst, you can always fall back on the old store it on a disk drive and take it home, but that's not ideal. I don't think the challenges we face, at least, and perhaps you're quite familiar with them, is we're facing competing demands from groups that don't necessarily have a good way of negotiating. You know, like the computing division of Department of Energy and the energy sciences, and how do they negotiate who has priority access to computers?
Thank you for the talk. The thing that struck me most, particularly towards the end, is the similarity between this and the continuous integration services that we all use, like GitHub Actions or the GitLab Actions.
Yeah.
Have you looked at how to integrate with any of those or steal any of the stuff they've already done?
Yes. No, we're quite familiar with those, and we make use of them ourselves. I think we haven't worked out yet how to use them directly for controlling experiments, but I think that there's probably more to be done there.
Okay. Do we thank the speaker again?
Okay, thank you.